Right now, while you're settling in, a comet 50 million kilometers away is falling toward the sun, not drifting, falling, at a speed that will make your mind go quiet just thinking about it. Comet 01 maps hasn't broken apart, hasn't flinched, and the sun it's diving into is carrying more stored magnetic energy than it has in weeks, aimed directly at Earth. 4 astronauts are preparing to leave the only magnetic shield humanity has ever known, on the same date the comet arrives. Nobody scheduled this, nobody designed it. It simply assembled itself around a single date, April 4th. Stay with me until the end, because what's converging on that date is not what anyone expected. If this has you hooked, subscribe to the Skylab because April 4th is 7 days away and we will be watching every second of it with you. And leave a comment. Tell me honestly, a giant comet, a stressed sun, an Earth-facing active region, 6 days of elevated radiation, and 4 astronauts heading beyond the shield, all converging on one date that nobody scheduled. If that is not the universe clearing its throat to get our attention, what exactly is it? Let's get into it. Part 1. 7 days. One date. 7 days from now, something is going to happen that has no modern precedent. Not because of what's coming, but because of when. On April 4th, at approximately 1425 UTC, a comet will reach the closest point in its journey around the Sun. That moment is called perihelion, and for Comet C/2026 A1, designated MAPS, perihelion is not a distant brush with solar warmth. It is a near collision with the most violent object in our solar system, at a distance of 0.005744 astronomical units from the solar surface. If that number means nothing to you, let me translate it into something that will. The Moon is 384,000 kilometers from Earth. This comet will pass within 50,000 kilometers of the Sun's surface. That is closer to the Sun than we are to our own Moon. It will be travelling through the solar corona, the outermost layer of the Sun's atmosphere, where temperatures reach 1 to 3 million degrees Kelvin. The radiation environment at that distance is roughly 40,000 times more intense than what Earth receives on its brightest day. There is no human technology designed to operate there. There is almost no natural object known to survive it. And yet, as of right now, Comet MAPS is intact. Its light curve, the measurement of how its brightness changes over time, is smooth. No sudden spikes, no fragmentation signatures, no asymmetry suggesting rotational breakup. For a comet of this type, that is unusual. Not impossible, but unusual in a way that matters, because it means we are 7 days away from watching a large, structurally coherent object enter one of the most extreme environments in the solar system. At a moment when that environment is anything but calm, here is where the story stops being about a comet. Right now, the Sun is carrying an active region on its face called AR4401. It sits near the centre of the solar disk at coordinates roughly north 25, west 02, which means it is aimed almost directly at Earth. Its magnetic classification is beta-gamma, which is the technical way of saying its magnetic field lines are tangled, stressed, and sitting at the threshold of instability. Forecasters are currently assigning it a 40% probability of producing an M-class flare. That is not a fringe number. That is a number that gets attention in space weather monitoring rooms, but AR4401 is not the only signal. For 6 consecutive days, satellites in Earth orbit have been measuring elevated 2 mega-electron-volt electron flux, high-energy electrons that indicate the radiation environment between the Sun and Earth is already running hot. Not from a single event, but persistently. A background hum that has been building. At the same time, a coronal hole high-speed stream is forecast to arrive, with KP index projections rising, which is the measure of geomagnetic disturbance that affects everything from power grids to GPS accuracy. And all of this is happening inside the spring equinox window, a period when Earth's magnetic geometry makes it more responsive to solar disturbances than at almost any other time of year. Now add the comment, none of these factors alone is a crisis. Let's be absolutely clear about that. An active sunspot is not unusual, elevated electron flux is not unusual, a coronal hole stream is not unusual, a sun-grazing comet is not unprecedented. But the combination, a large intact comet entering a magnetically stressed, radiation-loaded, geomagnetically coupled solar system, at the exact moment all of these variables are simultaneously elevated. That combination is what makes the next 7 days worth watching very carefully. The comet has not changed. Its trajectory is exactly what was predicted. Its structure appears stable. What has changed is the environment it is flying into, and in complex systems the environment is often the variable that matters most. Scientists tracking this event are not panicking, but they are paying attention in a way that is different from routine monitoring. The question being asked in observatories and space weather centres right now is not simply, will the comet survive? The question is, what happens when a large, intact, plasma-generating object enters a solar system that is already loaded, and whether the timing of that entry could matter in ways we have not fully mapped? That question doesn't have a clean answer yet. And that is precisely why, over the next 7 days, the eyes of some of the most serious solar scientists on Earth will be pointed at a single point in space. The comet hasn't blinked, but the sun has been stirring for days, and on April 4th those two facts are going to collide in the same location at the same moment for the first time in the modern era of solar observation. What happens next depends on something we still do not fully understand, and we are about to find out. Part 2. The object that shouldn't still be intact. Most comets that get close to the sun never make it to the headlines. They are detected as faint smudges in telescope imagery, tracked for a few days, and then they vanish, evaporated, fragmented, or simply outgassed into nothing before they ever reach the inner solar system. The graveyard of failed sungrazers is immense and largely invisible. We see the ones that make it, not the ones that don't, which is exactly why the detection history of comet maps tells us something important. It was first identified on January 13, 2026. That date matters more than it might seem. Detection distance is not just a logistical detail, it is a proxy for size. The further from the sun a comet is spotted, the brighter it must be at that distance to register in our instruments. And the brighter it is that far out, the more material it must be shedding, which generally means a larger nucleus driving the outgassing. For a Kreutz sungrazer, the family of comets to which MAPS belongs, early detection is rare. Most Kreutz fragments are not seen until they are already deep into the inner solar system, sometimes less than a week from perihelion. MAPS was detected when it was still months away. That is not normal for this family, that is a signal. The Kreutz sungrazers are fragments of what was almost certainly a single enormous parent comet that broke apart somewhere in the distant past, some researchers believe during a perihelion passage in the year 361, possibly compounded by another fragmentation event centuries later. What we observe now are the descendants of that breakup. Pieces ranging from a few meters across to objects potentially hundreds of meters, or even kilometers in scale, all following similar orbital paths, all diving toward the sun on inherited trajectories. The Great Comet of 1843 was a Kreutz sungrazer. So was the Great September Comet of 1882. So was Comet C, which in 1965 reached a brightness visible in daylight and left observers across the world genuinely unsettled. What all of those historic objects had in common was scale. They were large enough to survive, or at least partially survive, the perihelion passage. They were large enough to produce dramatic visual events. And they were detected early, because large objects are bright objects. MAPS fits that pattern. Its light curve since detection has been tracking a smooth, progressive brightening, exactly what you expect from a large nucleus outgassing at a controlled rate as it falls toward the sun. There have been no sudden jumps in brightness, which would suggest fragmentation events releasing large new surface areas. There has been no rotational asymmetry in the coma, the cloud of gas and dust surrounding the nucleus, which would suggest a tumbling or breaking body. By every external measurement we currently have, the nucleus of MAPS is intact, and it is large. Current brightness estimates put it in the magnitude 7 to 8 range, which is below naked eye visibility but well within the reach of binoculars and small telescopes. For context, most Kreutz sungrazers are never visible at all without spacecraft instruments. The fact that backyard astronomers can currently track MAPS is itself a statement about its size. But here is the part that doesn't get discussed enough. Structural integrity at 0.3 astronomical units, where MAPS currently sits, does not guarantee structural integrity at 0.005 astronomical units. Those two environments are not comparable. They are not even on the same scale of hostility. The forces acting on a comet nucleus at 0.3 astronomical units are significant but manageable for a large cohesive object. The forces at 0.005 astronomical units, inside the corona, inside the zone of tidal disruption, inside a radiation environment that strips electrons from atoms, are of a categorically different magnitude. And the comet is not experiencing those forces gradually. It is approaching them at a velocity that will become extreme in the final hours. Think of it this way. The fact that a building is still standing after 6 months of mild wind does not tell you much about how it will behave in a direct tornado strike. The evidence of survival under moderate stress is not evidence of survival under catastrophic stress. For comet maps, every day of smooth brightening is encouraging. But the real test has not started yet. There is a concept that solar scientists use when thinking about intact sungrazers, which might be called stored stress. Over months of infall, a comet nucleus accumulates internal stresses from 3 sources simultaneously: thermal stress from increasing radiation, tidal stress from the growing gravitational gradient as it approaches the Sun, and rotational stress from the torques applied by asymmetric outgassing. In a comet that fragments early, these stresses release gradually, small pieces break off, the structure reorganizes, and by the time it reaches perihelion it is already dispersed. In a comet that stays intact, those stresses do not release. They accumulate, they build, they wait. A comet that reaches the corona intact is, in a sense, a comet that has been holding its breath for months, and the corona is where it finally has to exhale. Whether that exhalation is quiet or catastrophic, whether it means a controlled tail dispersion, or a sudden, explosive release of stored energy into the solar magnetic field, is something that cannot be determined from the light curve alone. What we know is that the structural strength required to stay intact this long is also the structural strength that makes the final interaction potentially dramatic. The stronger it is, the more the material reaches the point of maximum stress. The more material that reaches maximum stress simultaneously, the more significant the interaction. Most Kreutz sungrazers never get to that point. They gave up early. They fragment in the outer corona or in the transition zone, or sometimes even before they enter the corona at all. The fact that MAPS appears to have not done is the reason this event is drawing attention from researchers who normally do not spend much time watching individual comets. The final 72 hours before perihelion are where sungrazers reveal their true nature, and right now, MAPS is still 7 days out, which means the question of what it actually is has not been answered yet. We're about to find out. Part 3. The last 72 hours problem. There is a law of orbital mechanics that most people learn in school and promptly forget because it sounds abstract. Johannes Kepler described it in the early 1600s, and it goes like this. A line connecting a planet, or a comet, to the Sun sweeps equal areas in equal times. What that means in practice is that the closer an object is to the Sun, the faster it moves. Not gradually faster, dramatically, non-linearly faster. For a comet on an orbit like MAPS, this creates a situation that is almost counterintuitive. Months of travel compress enormous distances at a manageable pace. Then, in the final days before perihelion, the trajectory changes character entirely. The last small fraction of the orbital path, the final few percent of the distance to be covered, is traversed at a velocity that dwarfs everything that came before. Objects in the outer solar system move at perhaps a few kilometers per second. Comets at perihelion can exceed 500 kilometers per second. In the final 72 hours, MAPS will cover more of its relative trajectory than it covered in the previous several weeks. The timeline collapses, the physics accelerates, and everything that was gradual becomes sudden. This is why the last 72 hours are not just the final phase of the event. They are, in a very real sense, the event itself. At those velocities, something begins to happen to the comet that does not occur at greater distances. As the nucleus, made of rock, dust, ice, and complex organic molecules, accelerates through the increasingly dense coronal plasma, its component atoms reach what physicists call the critical ionization velocity. This is a threshold, the speed at which neutral atoms interacting with a magnetized plasma become ionized. Below the threshold, the comet is chemically and electrically what it has always been, a cold body outgassing into space. Above the threshold, the comet begins to transform. Its material stops behaving like dust and ice and starts behaving like plasma. This transition is not gradual. It is threshold dependent, meaning it happens relatively sharply once the velocity crosses the critical point. And once it happens, The comet is no longer simply a physical object travelling through the solar environment. It becomes a charged particle source, a moving injection point for plasma directly into the Sun's magnetic field. And the Sun's magnetic field does not ignore new plasma sources. This is the central thread that runs through everything that follows. A comet that has stayed intact until this moment, that has stored stress rather than releasing it gradually, arrives at the corona not as a passive traveller but as an active participant in the solar magnetic system. It begins to interact, it begins to couple. The magnetic field lines threading through the corona do not simply let it pass, they respond. And the character of that response depends heavily on the state of the magnetic system the comet is entering. Which brings us back to where we started. The state of the Sun on April 4th is not neutral. It is not a quiet background against which the comet's interaction will play out invisibly. It is a system that is already carrying elevated stress across multiple independent indicators. The electron flux has been running high for 6 days. A complex active region is sitting near disk center. A high-speed stream is incoming. These are not decorative details. They are measurements of a system that is closer to threshold than it has been in recent weeks. A system that has less margin to absorb a perturbation than it would on a quiet day. In the final 72 hours, the comet will be generating plasma and coupling to magnetic field lines, while simultaneously experiencing the maximum radiation heating, the maximum tidal stress, and the maximum rotational torque it has ever encountered. All three of these forces peak simultaneously, not because of some cosmic coincidence, but because they all scale with proximity to the Sun. And proximity to the Sun is exactly what the final 72 hours are about. Think of it like this. You can stress a metal bar gradually for months, heat it, bend it slightly, cool it, repeat, and it may appear unchanged, but every cycle leaves microscopic damage. Then you apply one final stress at the moment of maximum accumulated damage, and the bar does not gradually deform, it snaps. The failure is not proportional to the final stress alone. It is the product of all the accumulated stress plus the final trigger. Comet MAPS has been accumulating stress since January. The final 72 hours are the final trigger. What happens in that window is not something any telescope on Earth can fully predict. The physics is known, the equations exist, but the specific outcome depends on variables, the exact internal structure of the nucleus, the precise configuration of the magnetic field at the moment of deepest penetration, the exact timing of any fragmentation events relative to the density of coronal plasma that cannot be measured remotely with the precision required to produce a confident forecast. What scientists can do is watch, in real time. Using SOHO and stereo imagery, coronagraph data, magnetogram readings from the Solar Dynamics Observatory, and a network of space weather monitors that will be running continuous observation from now through April 7th. This is not a passive flyby. That framing fundamentally misrepresents what is about to happen. This is an active interaction between a large plasma-generating object and a magnetically loaded solar system, occurring at maximum velocity in the most extreme radiation environment in the solar system, at a moment when the Sun is carrying more stored energy than it has in recent weeks, and it starts in earnest in about 72 hours before April 4th, which means the countdown is already running, and the three possible ways this ends are not what most people think they are. Part 4. Survival is not survival. If you look up past sun-grazing comets and ask what happened to the ones that survived, the first name that usually comes up is Comet Lovejoy, Comet C/2011 W-3. And the story of Lovejoy is instructive, but not in the way it is usually told. In December of 2011, Comet Lovejoy flew through the solar corona at a perihelion distance of approximately 140,000 kilometers from the solar surface, closer than maps will come, by some measures, though the comparison is complicated by orbital geometry. Virtually every model predicted it would not survive. The nucleus was estimated to be relatively small, perhaps a few hundred meters across. Pre-perihelion, many solar scientists were treating it as essentially a guaranteed disintegration event. Then it came out the other side. Imagery from SDO and stereo showed a surviving structure emerging from behind the Sun, trailing a dramatically brightened tail that persisted for days. It was described in headlines as a miraculous survival. Scientists were genuinely surprised. The comet appeared to have made it. But here is what those headlines did not explain. The nucleus of Lovejoy did not survive intact. What emerged from perihelion was a remnant, a fraction of the original mass, heavily processed, with most of the structural cohesion of the original body gone. The tail was spectacular precisely because an enormous amount of material had been injected into the solar corona. The survival was a survival of some portion of some material above some detection threshold, not the preservation of the object. Think of it like asking whether a candle survived a blowtorch. If there is still a small flame afterward, technically yes. But the candle is not what it was. For maps, this scenario, the Lovejoy scenario, represents what might be called the best visual outcome. A dramatic brightening at perihelion, a post-perihelion tail that persists for days, possible naked-eye visibility, extraordinary imagery from solar observatories. It is the scenario that produces the most spectacular footage. But it is not a scenario where the comet passes through unchanged. It is a scenario where the comet deposits an enormous amount of material into the corona, drives a significant plasma injection event, and what we call survival is really just the residual glow of a massive interaction. The probability is low to moderate. The physics can accommodate it for a large, structurally strong nucleus. But even in this outcome, the best case, the one that gets shared on social media as a triumph, the central question of how a large plasma injection interacts with the current solar magnetic environment remains fully in play. Because the comet does not travel through the corona without leaving a mark, it cannot. Conservation of energy, conservation of momentum, the fundamental properties of magnetized plasma, none of these laws take a day off for a photogenic comet passage. Material injected into the corona becomes part of the corona. Plasma coupling means the comet's charged particles follow magnetic field lines, and field lines connected to an active region, like AR4401, are not inert wires. They are loaded with springs. The best visual outcome is not the most scientifically quiet outcome. It might in fact be the scenario that produces the most interaction, because it means the nucleus reached maximum depth before releasing its material in a single concentrated burst. A large intact body reaching 0.005 astronomical units before fragmenting is a more concentrated plasma source than a body that disperses at 0.1 astronomical unit. Which means the question shifts. Not did it survive, but what did survival cost the Sun? And that question leads directly to the second scenario, the one that looks less dramatic on camera, but may be more physically significant than it appears. Part 5. Fragmentation isn't harmless. The most statistically likely outcome for comet maps is not survival and not complete vaporization, it is fragmentation. Say that word slowly for a moment, because most people hear it and immediately picture the anticlimactic version, a comet quietly crumbling into dust, dispersing harmlessly, the solar system tidying up after itself like nothing happened. That instinct is understandable, it is also wrong. And the gap between what fragmentation sounds like and what fragmentation actually does, for a nucleus the size of maps, is where this story takes a turn that almost nobody is talking about. First, the baseline. This is what Kreutz sungrazers typically do. The historical record, both modern spacecraft observation and pre-telescopic accounts, interpreted through orbital dynamics, shows that the majority of Kreutz family members break apart before or during perihelion. Not cleanly, not all at once, but progressively. Pieces carving off the main body, subnuclei separating along internal fault lines that have been accumulating stress for months. The coherent structure of the original object giving way, gradually and then suddenly, to a distributed cloud of fragments, each continuing on the shared trajectory but no longer acting as a single unit. It is less like a clean break and more like a building whose load-bearing walls have been quietly cracking since January, finally deciding that the structural pretense is no longer worth maintaining. For most of the sungrazers observed by SOHO since its launch in 1995, this fragmentation is the final act. The comet brightens as new surface area is exposed, shows signs of structural instability in the light curve, breaks into pieces, and the pieces vaporize in sequence as they each reach their individual perihelion moments. What is left is a broad, diffuse smear of material strung along the orbital path, visually anticlimactic compared to a single bright nucleus, scientifically interesting in a catalogue entry sort of way, and generally logged without alarm. Most SOHO sungrazers are small. Most SOHO sungrazers don't make headlines even when they are behaving unusually. Most SOHO sungrazers are not maps, and this is the part that changes everything. When a comet nucleus fragments, the primary physical effect is an increase in total surface area. This sounds like a minor technical detail. It is not. Consider the geometry. A single sphere of a given volume, when broken into smaller pieces, exposes dramatically more surface area to its surrounding environment than the original intact body. If you take that sphere and break it in half, you have created two new faces of exposure. Break it into 10 pieces, and the exposed surface multiplies further. Break it into 100 pieces of varying sizes, as a fragmenting comet nucleus actually does, and the total surface area interacting with the surrounding corona increases by an amount that is not incremental. It is transformative. More surface area means more material sublimating, evaporating and ionizing in direct contact with the coronal plasma. More ionization means more charged particles injected into the sun's magnetic field, and more plasma injection into the magnetic field means a larger perturbation to the system the comet is passing through. The arithmetic here runs in the opposite direction from what intuition suggests. Fragmentation does not reduce the scale of the Sun-comet interaction. For a large nucleus, it can increase it, while simultaneously spreading that interaction across a broader spatial area and a longer temporal window. This is the counterintuitive heart of the fragmentation scenario, and it deserves to sit with you for a moment before we move on. The distribution of material across multiple fragments means the plasma injection is not concentrated at a single point during a single moment of maximum perihelion depth. A single intact nucleus reaches perihelion, interacts, and the event is geographically and temporally discrete. A fragmented nucleus, by contrast, produces a plasma injection that is smeared across a window of time, potentially covering a wider arc of the coronal magnetic field, creating multiple smaller coupling events rather than one large concentrated one. The total material involved may be similar. The pattern of interaction is entirely different. Here is the analogy that makes this concrete. One large stone dropped into a still pond creates a single set of concentric ripples, predictable and symmetric, radiating outward from a single point. Take that same stone, break it into a dozen pieces, and drop them all into the pond simultaneously but at slightly different points. What you get is not smaller versions of the original ripple pattern. You get overlapping wave systems that interfere with each other, creating regions of constructive interference where the waves amplify, and regions of destructive interference where they cancel. The total energy in the system is identical. The geometry of where that energy concentrates is completely different, and in a nonlinear system, geometry determines outcome. The sun's corona is not a still pond. It is an extraordinarily complex dynamic magnetized plasma environment, but the principle translates. Field lines respond locally to perturbations. A perturbation distributed across a magnetically complex region interacts with that region differently than a concentrated point source would. Whether the distributed interaction is more or less disruptive than the concentrated one is not a question the physics resolves cleanly in advance. It depends on the specific structure of the magnetic field the fragments encounter, the timing of each individual fragment's outgassing peak, and the existing state of stress in the regions those field lines thread through, which on April 4th includes AR 4401. That detail does not become less important just because we are now discussing a fragmentation scenario rather than an intact nucleus scenario. If anything, a distributed plasma injection across a wider coronal arc increases the probability that some portion of that injection couples to the field lines threading through and around the active region. A single point source might miss. A distributed source covering a broader arc is harder to miss with. There is also a timing dimension that rarely gets the attention it deserves. Fragmentation that occurs 24 to 48 hours before perihelion, which is the typical window for Kreutz objects based on historical observation, means that the individual fragments do not simply vaporize instantly. They have time, in the hours between separation and their individual perihelion moments, to develop their own comas. Each fragment begins its own outgassing process. Each one starts generating its own localized plasma contribution. By the time the first fragments reach perihelion, the later separating fragments are still in the process of developing their individual interaction signatures. The overall event is not a single discrete occurrence. It is a sequence, an extended, distributed, overlapping series of plasma injection events, each contributing to a coronal perturbation that persists longer than any single nucleus interaction would. This brings us to a quiet implication that almost never gets stated directly in public coverage of sun-grazing comets, but that matters enormously for understanding what April 4th could actually look like. The fragmentation scenario might produce a longer interaction window than the survival scenario. A comet that stays intact, reaches perihelion, and either partially survives or vaporizes completely does so quickly. The interaction is sharp and brief, a single concentrated event at the moment of maximum solar proximity. A comet that begins fragmenting 24 to 48 hours before perihelion, with each piece developing its own coma and contributing its own plasma injection on its own schedule, could drive a persistent perturbation across a wider region of the corona for a period of time that extends well beyond the perihelion moment itself. The energy input is not larger, the duration and spatial distribution of that input are. So is fragmentation the quiet scenario? Is it the outcome that solar physicists should feel relieved about? The evidence that the comet did not hold together long enough to deliver a concentrated payload? The honest answer is, we do not know, and that uncertainty is not a failure of the science, it is what the science actually says. The outcome depends on variables: the precise timing of fragmentation relative to the magnetic configuration of the corona, the size distribution of the resulting fragments, the specific field line geometry at the moment of each fragment's perihelion, that cannot currently be resolved from remote observation alone. What can be said with confidence is that the three possible outcomes, survival, fragmentation, and the third scenario we have not yet named, are not cleanly ranked from most to least disruptive. They do not sit in a tidy hierarchy where survival is the worst case and fragmentation is the safe middle ground. The relationship between outcome and consequence is more complex than that, more geometry dependent, more sensitive to the specific conditions of the environment the comet encounters than to the fate of the nucleus itself. And the third scenario is the one that sits at the intersection of all the threads we have been following, the one that requires a specific combination of conditions to be plausible, the one that solar physicists will tell you, carefully and correctly, has not been proven, the one that nevertheless, on this particular date, with this particular sun, with this particular configuration of active regions and radiation stress and geomagnetic coupling, cannot be cleanly dismissed. That is the scenario we need to talk about next. And it starts not with the comet at all, but with what the sun was already doing before the comet arrived. Part 6. The Trigger Hypothesis. Let's be direct about what this section is and what it is not. What follows is a hypothesis, not a prediction, not a breaking news alert, not a consensus position from the solar physics community delivered with institutional confidence. It is a mechanism, one that has been proposed, studied, discussed in peer-reviewed literature, supported by correlational evidence, and not confirmed as causal. The scientists who have studied it most carefully will tell you exactly that, in exactly those words. The correlations are real, the mechanism is physically plausible, the causation has not been established. Hold that clearly in mind as we go through this, because the hypothesis is genuinely interesting on its own terms, without any exaggeration, and it does not need to be oversold to matter. Here is the hypothesis. A large sun-grazing comet, arriving at perihelion in a region of the solar corona where magnetic flux ropes or filaments are already near their stability threshold, could provide the perturbation, the trigger, that initiates a release of energy the sun was already storing. Not by delivering energy from outside, not by injecting something the sun does not already have, not by overloading a stable system with an external force, but by nudging an already unstable system across the line. It was already approaching on its own schedule, on its own terms, toward an outcome that was always coming, with the comet simply deciding when. That distinction matters more than it might initially seem, so let's stay with it. The sun is not a passive object. It is an engine. It generates magnetic field continuously, twists and braids that field through the motion of plasma across its surface, and stores the resulting magnetic energy in structures threaded through the corona. Magnetic flux ropes, tightly wound, twisted bundles of field lines held in place by the surrounding magnetic pressure, can accumulate energy for days or weeks without releasing it. Filaments, dense regions of cooler, heavier plasma suspended above the solar surface by magnetic tension, like hammocks strung between field line anchors, can persist for extended periods in apparent stability before the tension holding them gives way and they erupt outward. In both cases, the stored energy is completely real. The instability building beneath the apparent calm is completely real. The question is never whether that energy will eventually release. It always does. The question is only when and what, if anything, tips the balance. Now here is where the physics of nonlinear systems enters the conversation, and this is the part that people sometimes dismiss as too abstract to be useful. It is not abstract. It is mechanistic. It describes, precisely and literally, how a large class of physical systems actually behaves. In a system that is at or near threshold, the trigger does not need to be large. It does not need to be proportional to the energy released. It does not need to contribute meaningfully to the event's total energy budget. This is the avalanche principle, and calling it a principle rather than a metaphor is correct. It describes the behavior of real physical systems, from snow slopes to electrical grids to biological neural networks. A snow slope in stable equilibrium, with friction forces comfortably exceeding gravitational ones, requires a significant disturbance to initiate movement. A snow slope that has already accumulated past its angle of repose, where the gravitational forces are already marginally exceeding the friction holding it in place, requires essentially nothing. A footfall, a vibration transmitted through the ground from a vehicle passing on a road a kilometre away, a change in air temperature of half a degree that slightly reduces the surface friction at the critical interface. In that second case, the trigger contributes almost nothing to the energy of the avalanche. The avalanche's energy comes entirely from the gravitational potential of the mass already sitting on the slope. The trigger is purely a timing mechanism. It decides when. It does not decide how much. Apply that now to the Sun on April 4th, and the picture assembles itself. R4401 is a beta-gamma magnetic region in an active growth phase. It is not a stable, mature sunspot group winding down toward the end of its life cycle. It is developing, penumbral structure expanding, magnetic complexity increasing, free energy accumulating in the tangled field lines between opposite polarity regions sitting in uncomfortably close proximity. The electron flux in near-Earth space has been elevated for 6 consecutive days, which is not the signature of a single energetic event that has passed and is now decaying. It is the signature of a sun that has been continuously feeding energy into the environment between itself and Earth for nearly a week without returning to baseline. A high-speed stream from a coronal hole is inbound, adding another perturbation to a system that has not had time to settle from the previous ones. Taken together, these measurements describe a sun that is carrying less margin than usual, a system closer to its own threshold than a quiet sun would be, not dramatically so, not certainly about to erupt, but measurably, observably, closer to the edge. Into that system, on April 4th, at approximately 1425 UTC, a large intact comet, or, if the fragmentation scenario has already begun, the distributed plasma remnants of a fragmenting comet spread across a wider coronal arc, injects charged particles directly into the corona. Those particles are not neutral, they are ionized, they carry charge. And charged particles in a magnetized plasma do not travel in straight lines and exit the system cleanly. They follow field lines. They couple to the magnetic structure they enter. Field lines threading through the corona near perihelion connect, in some configurations, to the active regions rooted in the solar surface below. Field lines connected to active regions thread through flux ropes. Flux ropes currently carrying stored magnetic energy that has been accumulating for days. The question the trigger hypothesis asks is whether the plasma injection from MAPS, arriving at this specific moment, in this specific configuration, could provide the perturbation that tips an already strained system over the threshold it was already approaching. Not a large perturbation, not an overwhelming one, just enough, just the footfall on the loaded slope. The researchers who have examined historical correlations between large sun-grazer perihelion events and subsequent solar activity give an answer that is carefully and correctly hedged, but not dismissive. Possibly yes, they say, in specific circumstances, for reasons that are physically plausible but not yet fully understood. There are cases in the historical record, not many, and not all cleanly documented enough to survive rigorous statistical scrutiny, where significant solar energetic events followed closely after major sun-grazer perihelion passages. The timing correlations are suggestive. They survive basic statistical testing. They are not noise. They are also not proof. And the gap between suggestive correlation and established causation is where most of the honest scientific uncertainty about this hypothesis currently lives. The range of outcomes the hypothesis admits runs across a very wide distribution. At one end, nothing detectable at the solar level. The comet completes its perihelion passage, injects plasma into the corona, and the system absorbs the perturbation without crossing any threshold. AR 4401 continues its evolution on its own schedule. The electron flux eventually returns to baseline, and the event is recorded as an interesting observation with no measurable solar consequence. That end of the distribution is populated by a large fraction of the probability. Moving along the distribution, a minor enhancement of flare probability in AR 4401, producing an M-class event somewhat earlier than its background probability alone would have suggested. Energetically modest, detectable, but not dramatic. The kind of event that gets a space weather advisory and a brief mention in monitoring reports. Further along, a significant M-class or X-class flare, potentially accompanied by a coronal mass ejection directed toward Earth, arriving in the April 5th to 7th window during the period of maximum equinox geomagnetic coupling. Meaningful space weather impact, satellite charging, GPS disruption, possible auroral activity at mid-latitudes, the kind of event that gets remembered in space weather records for the year. At the far tail of the distribution, low probability, clearly stated not to be weighted as a central scenario, a coronal mass ejection of major scale. The Carrington comparison is the reference case that solar physicists use when they want to describe what the far tail of solar event magnitude looks like. The 1859 Carrington event remains the most intense solar storm in the historical instrumental record. If a comparable event struck Earth today, the consequences for power infrastructure, satellite systems, communications networks, and anything dependent on stable electromagnetic operating conditions would be severe and widespread in ways that modern society, far more dependent on those systems than 1859 society was, has never experienced. That scenario sits at the extreme tail of the distribution for April 4th. Its probability is not zero. Assigning it a specific number would require a level of confidence in the trigger mechanism that the current science explicitly does not support. What can be said is that the conditions on April 4th represent the most favourable alignment for the trigger hypothesis to be observable, that the modern era of solar science has assembled around a single event, not because the comet is uniquely enormous, not because the sun is uniquely violent, but because the specific combination, comet structural integrity at this stage of approach, active region position and magnetic classification, radiation environment persistence, geomagnetic coupling window, creates a density of simultaneously elevated variables that researchers tracking this mechanism have not seen concentrated around a single perihelion event in recent memory. And that density is why April 4th is something closer to a natural experiment than a routine observation. If the correlation holds, if what follows perihelion includes a significant solar event within the time frame the mechanism predicts, it will not prove causation. But it will make the case for taking the hypothesis seriously in a way that isolated correlations in the historical record have not yet achieved. If nothing happens, that result carries its own scientific value. It constrains the mechanism. It places limits on the conditions under which the trigger can operate. Either way, the data generated by this event is data the hypothesis has needed for a long time. Now look at what the comet is actually flying into. Because the active region sitting at the centre of all these threads, AR 4401, has been receiving far less attention in general coverage than its current configuration warrants. What is happening there right now is not routine, and it deserves to be looked at directly. Part 7. AR 4401, a loaded configuration. Active regions are a normal feature of a solar maximum sun. They appear regularly, evolve over days to weeks, and most produce nothing more dangerous than a modest flare that barely registers on Earth-based sensors. A brief brightening in the extreme ultraviolet, a minor uptick in the X-ray flux, a note in the daily space weather bulletin that most people never read. The sun has them constantly. They are, in the language of solar monitoring, routine. AR 4401 is not currently in that category. And to understand why, it helps to understand what actually makes an active region dangerous, not just technically, but physically, mechanically, in terms of what is actually happening in the magnetic structure beneath the sunspot group we can observe from Earth. Sunspots are not simply dark patches on the solar surface. They are the visible signatures of magnetic field lines punching through the photosphere, the visible surface layer of the Sun, with enough intensity to suppress the convective heat transport that normally keeps the surface bright. Where the field is strong enough, the plasma cannot circulate freely, heat transfer is reduced, and the region appears darker than its surroundings. The spots themselves are just the symptom. The magnetic structure threading through and above them, extending up into the chromosphere and corona, is where the energy lives. And the character of that magnetic structure, its complexity, its polarity distribution, its degree of mixing, determines how much energy is stored and how violently it can be released. The classification system solar physicists use to describe active region magnetic complexity runs from simple to extraordinarily tangled. At the simple end, alpha regions have a single magnetic polarity, one coherent bundle of field lines, no mixing, minimal free energy, minimal flare potential. At the complex end, delta regions have opposite polarity umbros sharing the same penumbra, field lines of opposing directions packed so tightly together that the boundary between them becomes a site of extreme magnetic stress. Between these extremes sit the beta and beta-gamma classifications, each representing increasing degrees of polarity mixing and field line entanglement. AR4401 currently carries a beta-gamma classification. That means it contains magnetic flux of both polarities in close proximity, with field lines that are not cleanly separated into tidy opposing bundles, but intermixed, interleaved in a configuration that physicists describe as carrying magnetic free energy. Free energy, in this context, has a precise meaning. It is the energy stored in the deviation of the magnetic field from its theoretical minimum energy state, the configuration the field would relax into if left undisturbed. The greater the deviation from that minimum energy state, the more free energy is stored, and the more energy is available for sudden release when the field reconnects toward a lower energy configuration. That reconnection event is what we call a solar flare. The free energy is the fuel. The magnetic complexity is the measure of how much fuel is present. For a beta-gamma region, the fuel supply is significant. Now add the first factor that distinguishes AR4401 from a routine beta-gamma region that happens to be present during solar maximum, its position. North 25, West 02. Those coordinates place it almost exactly at disk center, the point on the solar surface that, at this moment in Earth's orbit, is aimed most directly at our planet. This matters in a way that is both simple and consequential. Solar flares produce radiation that travels at the speed of light in all directions from the source. Coronal mass ejections, the plasma clouds launched by major flares, travel outward from the source along a trajectory largely determined by the geometry of the event. A flare or CME originating from a region near the solar limb, the edge of the visible disk as seen from Earth, produces an event that travels largely sideways relative to Earth's position. We might catch the edge of it, experience a glancing blow, register a modest geomagnetic disturbance. A flare or CME originating from disk center produces an event that travels along the Sun-Earth line. It does not clip us at an angle, it does not pass by at a distance, it travels in a straight line toward the planet, and Earth is what it hits. The geometry of AR4401's current position is, from a space weather standpoint, about as direct as it is possible for an active region to be. If this region produces a significant event in the coming days, the directionality question is already answered. It is pointed at us. Whatever it produces, we are in the path. The second distinguishing factor is the one that makes the timing relevant rather than simply the position. AR4401 is in a growth phase. This is not a region that has already peaked in complexity and is now slowly decaying toward a simpler, lower energy configuration, the normal trajectory of a sunspot group in the latter half of its life cycle. The penumbral development, the growth of the darker outer portions of the sunspot group that reflect the expansion of the underlying magnetic structure, has been continuing. New flux is emerging. The region is not releasing its stored energy gradually through a series of minor events and then dissipating. It is building. The magnetic free energy inventory of this region is not being drawn down, it is being added to. A growing active region is a region that is moving toward greater instability, not away from it. Every day of continued development means more free energy, stored in a more complex field configuration, with more potential for a sudden large-scale reconnection event. The 40% M-class flare probability currently assigned to this region by space weather forecasters is not a fixed number. It is a snapshot of the region's current state. If the growth phase continues through April 4th, that probability has room to increase, not guaranteed to increase, but the trajectory of development points in that direction. 40%, incidentally, is not a background number. On a quiet sun with no particularly notable active regions, M-class flare probability on any given day is a small fraction of that. 40% reflects a region that forecasters are actively watching, that has crossed the threshold from routine monitoring to elevated attention. It is the kind of number that generates internal discussions at space weather prediction centers. It is not by itself an emergency, but it is not nothing. Now hold all of that, the position, the classification, the growth phase, the flare probability, and place it in the context of what we've been building throughout this story. The region that sits at the geographic intersection of the comet's perihelion trajectory is not a quiet, stable, declining sunspot group that happens to be in the wrong place at the wrong time. It is a loaded, growing, Earth-facing magnetic structure that is already being independently monitored for its own reasons, entirely separate from anything to do with the comet. Space weather forecasters would be watching AR4401 this week regardless of whether comet maps existed. The active region has earned that attention on its own merits. The comet does not need to trigger anything. That point deserves to be stated plainly and without qualification. AR4401 may produce a significant event, an M-class flare, an X-class flare, a coronal mass ejection directed along the Sun-Earth line, entirely through its own internal dynamics, on a timeline driven purely by the continued evolution of its magnetic structure, with no input from any external perturbation whatsoever. The region is capable of that independently. The probability is already elevated independently. But the question the trigger hypothesis raises, and it is, to be clear, a hypothesis, not a certainty, not even a strong consensus probability, is whether a plasma injection from MAPS, arriving at this particular region's field line structure at the moment of perihelion, changes something, not creates something, changes something, alters the timing of an event that was already approaching, shifts the magnitude of a release that was already accumulating, provides the perturbation that moves the threshold crossing from sometime later this week to the afternoon of April 4th. That question cannot be answered in advance with the observational data currently available. The internal magnetic structure of AR4401 at the scale required to assess its precise proximity to threshold is not directly measurable from Earth-based or near-Earth instruments. The exact configuration of the coronal field lines the comet plasma will couple to during perihelion passage cannot be resolved at the required precision before the event. The trigger hypothesis, even in its most carefully stated form, does not produce a testable prediction precise enough to say definitively whether it applies on this specific date. What it produces is a framework, a set of conditions under which the mechanism could operate. And what the data says about those conditions right now, the beta-gamma classification, the growth phase, the disk center position, the elevated electron flux that has been running for nearly a week, the incoming coronal hole stream, the equinox coupling window, is that they are present. Not all of them at hypothetically maximum intensity, but all of them, simultaneously, pointing in the same direction, assembled around the same date. The system surrounding AR4401 has been in an elevated state for long enough that the normal baseline no longer applies cleanly. The region is not behaving like background solar activity. It is behaving like a system that has been building towards something. Whether that something arrives on its own schedule, or whether the comet's arrival on April 4th becomes part of the story of when and how it arrives, is a question that only the next several days can answer. And the electron flux data, 6 days of persistent elevation with no return to baseline, is telling us that the system has been holding this elevated state through multiple solar rotations of AR4401's development. Whatever is building there has been building for a while. The comet is arriving not at the beginning of that build-up, but near what may be its peak. That timing, again, is not designed. It is not coordinated. It is simply what the data shows. And the data is worth taking seriously on its own terms before we add the next layer, the radiation environment that has been quietly running hot in the background of all of this, for reasons that connect back to the same solar state driving everything else we have been discussing. Part 8. The quiet signal that isn't quiet. 6 days. That number sounds modest. It does not have the drama of a solar flare designation or the visual immediacy of a coronagraph image showing plasma erupting from the solar surface. 6 days of elevated electron flux does not produce a news alert. It does not generate a public advisory. It sits in the monitoring data, logged continuously by instruments aboard satellites in near-Earth space, noted by the engineers and space weather analysts whose job it is to watch these numbers, and largely invisible to everyone else. But 6 consecutive days of elevated 2 MeV electron flux is not a minor footnote in the current solar picture. It is one of the most diagnostically significant pieces of data in the entire convergence we have been assembling. And to understand why, it helps to understand what 2 MeV electrons actually are, where they come from, and what their sustained presence tells you about the system producing them. 2 MeV electrons are high-energy particles, electrons accelerated to energies of 2 million electron volts, which places them firmly in the category of radiation that spacecraft engineers take seriously. They are not the same as the lower energy electrons that make up the bulk of the solar wind under normal conditions. They are relativistic particles, moving at a significant fraction of the speed of light, capable of penetrating spacecraft shielding, depositing charge on internal components, and gradually degrading the electronics and materials they interact with. The effect is not instantaneous. A single day of elevated 2 MeV flux does not disable a satellite. But sustained exposure over multiple days begins to accumulate in ways that matter to the operational lifetime and reliability of the systems being irradiated. Satellite operators use a threshold of roughly 1,000 particle flux units, particles per square centimetre per second per steradian, as the level at which they begin paying closer attention to charging risk. At 10,000 particle flux units, which is where peak readings have been sitting during this 6-day elevated period, the risk level is not theoretical. It is the kind of environment in which anomalous behaviour in sensitive spacecraft systems becomes statistically more likely. Operators of high-value assets in geostationary orbit, communication satellites, weather satellites, navigation infrastructure, have procedures for elevated flux environments. Those procedures are not idle protocols. They reflect real engineering experience with what sustained high-energy electron environments do to hardware that was designed and tested under normal operating assumptions. But the engineering concern, real as it is actually the less interesting dimension of what the 6-day electron flux elevation is telling us. The more important dimension is diagnostic. Electron flux at these energies does not simply appear. It is produced by specific physical processes in the Sun-Earth system, primarily the acceleration of particles in regions of magnetic reconnection and wave-particle interaction in the inner heliosphere. The presence of sustained elevated flux over multiple days means that the Sun has been continuously driving particle acceleration processes, not in a single burst that then decays, but persistently, maintaining the output above baseline through a period long enough to encompass multiple solar rotation increments of the active regions on the disk. The system has been in a state of elevated energy output for nearly a week, and critically, it has not returned to baseline between individual events. This is the distinction that changes the interpretation entirely, and the medical analogy is the most direct way to convey it. A fever that spikes to 39 degrees Celsius, breaks overnight, and returns to normal by morning tells you something very different about the underlying condition than a fever that has been running at 37.8 for 6 days without resolution. The peak temperature in the first case is actually higher, but the second case is the one that worries a physician more, because duration implies that the underlying process generating the fever has not been resolved. The body has not returned to equilibrium. Something is maintaining the elevated state. And a system that cannot return to equilibrium between perturbations is a system with less capacity to absorb the next perturbation when it arrives. Apply that reasoning to the Sun-Earth radiation environment, and the 6-day electron flux elevation stops looking like background noise and starts looking like a system that has been continuously stressed for long enough that its baseline has effectively shifted upward. The normal reference point, the level of activity that space weather forecasters use as a baseline for assessing whether current conditions are elevated, is a level this system has not returned to in nearly a week. Every new event, every new injection of energy from the Sun is building on a foundation that is already above its resting state. Now place that in the context of everything else we have been tracking. The electron flux elevation, the beta-gamma active region in a growth phase at disk center, and the incoming coronal hole high-speed stream are not three separate stories happening to share a time window. They are not independent processes that happen to be running concurrently by coincidence. They are different instruments measuring different aspects of the same underlying condition, a sun that is running hot across multiple simultaneous parameters in a way that has been sustained rather than transient, during a period that is approaching a perihelion event of unusual character. Think of it as multiple gauges on the same engine. The temperature gauge, the oil pressure gauge, and the RPM indicator are measuring different things, but when all three are simultaneously elevated and have been for an extended period, the interpretation is not that three separate minor issues are present. The interpretation is that the engine itself is in an elevated operating state, and that all three gauges are reflecting the same underlying condition from their respective vantage points. In that situation, adding a new load to the engine is not the same as adding that same load to an engine running at normal operating temperature with normal pressure and normal RPMs. The margin for absorption is lower. The probability of a response that exceeds normal parameters is higher. The Comet is arriving at an engine that has been running hot for 6 days, not at a red line, not at a point of imminent catastrophic failure, but measurably, persistently above its resting state, in ways that multiple independent instruments are simultaneously confirming. This matters for the trigger hypothesis we discussed in detail previously, because the trigger hypothesis does not require a sun at maximum instability. It requires a sun closer to threshold than baseline, a sun with measurably reduced margin to absorb a perturbation without crossing into a different response regime. A sun running at elevated electron flux for 6 consecutive days, with a growing beta-gamma active region at disk center, with an inbound high-speed stream adding another perturbation layer, is precisely the description of a sun with reduced margin. Not zero margin, but less than normal, and the Comet is not arriving at the beginning of this elevated period. It is arriving near what may be its peak, after 6 days of accumulation, at the moment when the stacking of incoming perturbations, the coronal hole stream, the active region development, the existing radiation environment elevation, is at its densest. The timing is not designed. Nothing about this is designed. But the timing is what the orbital mechanics and the solar physics have produced, and the timing is what matters. There is also a subtler point embedded in the 6-day duration that deserves to be made explicit. Sustained particle flux elevation of this kind is associated with the presence of what space weather physicists call a high-speed stream interaction region, a zone where faster solar wind emanating from a coronal hole catches up with slower solar wind ahead of it, compressing the plasma and magnetic field at the boundary and creating conditions favourable for particle acceleration. These interaction regions are efficient particle accelerators. They also carry with them enhanced magnetic field strength and increased solar wind pressure that, when they encounter Earth's magnetosphere, drive geomagnetic activity. The coronal hole high-speed stream currently inbound is not arriving into a quiet magnetospheric environment. It is arriving into a magnetosphere that has already been processing elevated particle flux for 6 days. The magnetosphere, like the solar environment generating the flux, has been working harder than normal for an extended period. Its capacity to absorb a new, stronger perturbation without significant response is not the same as it would be on a quiet day following a quiet week. All of which means that the Earth the Comet's perihelion effects will ultimately reach, through whatever solar response occurs at the Sun, travelling across the 1.5 million kilometres to the L1 point and then onto Earth, is not a planet sitting in a neutral, well-buffered space environment. It is a planet whose near-space environment has been running elevated, whose magnetosphere has been continuously processing above normal particle flux, and whose geomagnetic response to any incoming disturbance will be shaped by the accumulated state of the past 6 days, rather than by a fresh, undisturbed baseline. And the magnetosphere's response to incoming solar disturbances is not constant across the year. It varies. It varies in a specific, predictable, well-documented way that is tied to Earth's position in its orbit. And right now, that variation is pointed in exactly the direction that makes everything we have been discussing more consequential for the planet on the receiving end. Because there is one more variable in this convergence that rarely gets the attention it deserves, one that has nothing to do with the comet, or the active region, or the electron flux. One that is driven purely by orbital geometry, by where Earth sits in its path around the Sun on this particular date. And it is the variable that connects everything happening at the Sun to what actually arrives at Earth's surface, in a way that makes the timing of April 4th more significant than the same events would be in July or December. That variable has a name, and once you understand what it does, the convergence stops feeling like a collection of interesting coincidences and starts feeling like something the calendar itself arranged. Part 9. The Equinox Effect. Twice a year, Earth's relationship to the Sun's magnetic field changes in a specific and measurable way. Not dramatically. Not in a way you would feel standing outside on a March morning compared to a July afternoon. The sky looks the same. The Sun looks the same. The magnetosphere, that invisible magnetic cocoon generated by Earth's internal dynamo, extending tens of thousands of kilometers into space in every direction, looks the same to any instrument casual enough to miss the subtlety. But the subtlety is real, it is quantifiable, and on the scale of space weather consequences, it is the difference between a solar disturbance that produces a minor geomagnetic storm and the same solar disturbance producing one that takes down power infrastructure. To understand why, you need to understand something about how Earth's magnetosphere actually interacts with solar wind and the magnetic field embedded within it. This is not intuitive physics, but it is not complicated once the geometry is clear. The solar wind, the continuous stream of charged particles flowing outward from the Sun in all directions, carries with it a magnetic field. This is the interplanetary magnetic field, and it does not point in a fixed direction. It rotates, it varies, it shifts orientation continuously as different regions of the Sun contribute to the outflowing wind. The component of this field that matters most for geomagnetic activity is its north-south orientation, what physicists call the BZ component, measured in the coordinate system of the ecliptic plane, the flat plane in which the planets orbit the Sun. When the interplanetary magnetic field points southward, when BZ is negative, it is oriented opposite to Earth's own magnetic field at the point where the solar wind meets the magnetosphere. Opposite pointing magnetic fields do something that aligned fields do not. They reconnect. Field lines from the solar wind couple to field lines from Earth's magnetosphere, opening a channel through which energy and particles from the solar wind can flow directly into the magnetosphere. This process is called magnetic reconnection, and it is the fundamental driver of geomagnetic storms. No southward BZ, no efficient reconnection, no significant geomagnetic storm regardless of how fast or dense the solar wind is. Strong southward BZ are sustained for hours, and the magnetosphere couples efficiently to the solar wind, energy pours in, and the consequences cascade down through the system. Now here is where the orbital geometry enters, and where the Russell-McFerrin effect becomes relevant. Earth's magnetic axis is tilted relative to the ecliptic plane, the plane of the solar system, by approximately 11 degrees. Earth's rotational axis is tilted by approximately 23.5 degrees. These tilts mean that the orientation of Earth's magnetic field relative to the incoming solar wind direction is not constant across the year. It changes slowly as Earth moves around its orbit, and twice a year, at the equinoxes, it reaches a configuration that is geometrically optimal for southward BZ coupling. The mechanism, as described by Christopher Russell and Robert McFerrin in their 1973 paper that gave the effect its name, works like this. The interplanetary magnetic field has a systematic tendency, driven by the geometry of the Sun's own magnetic structure and the Parker spiral shape of the solar wind, to have a component that points in a particular direction in the ecliptic plane. At the equinoxes, the orientation of Earth's magnetic dipole relative to that systematic component reaches its most favourable angle for producing the southward BZ that drives reconnection. The same solar wind carrying the same interplanetary magnetic field arriving at Earth at the equinox produces more southward BZ in the geocentric coordinate system, the coordinate system that determines how much reconnection actually occurs, than it would arriving at the solstice. Not because the solar wind changed, because Earth's orientation changed. The practical consequence is a seasonal modulation of geomagnetic storm frequency and intensity that has been documented in the historical record going back well over a century. Statistical analysis of geomagnetic storm occurrence shows a clear enhancement in March and April, and again in September and October, centered on the equinoxes. The effect is not subtle in the statistics. Storms that would be classified as moderate at the solstice are more likely to reach severe classification during the equinox windows. The same solar input processed through a more favourably oriented magnetosphere produces a stronger output. April 4th sits approximately 2 weeks past the spring equinox of 2026, which fell on March 20th. The Russell-McPherron enhancement window is typically described as spanning roughly 2 to 3 weeks on either side of the equinox, meaning the peak of the enhancement window extends from approximately March 6th through April 3rd or 4th, with the trailing edge of elevated coupling efficiency persisting for some days beyond that. April 4th sits at or very near the trailing edge of the primary enhancement window, not at the absolute peak, which was closer to the equinox itself, but well within the period of elevated geomagnetic response efficiency. The coupling enhancement has not yet dissipated to its baseline level. What this means in concrete terms is straightforward to state and important to sit with. Any coronal mass ejection produced by the Sun in the coming days, whether driven by the independent evolution of AR4401, by the arrival of the coronal whole high-speed stream, by a plasma injection event associated with the comet's perihelion passage, or by some combination of these factors, will arrive at an Earth whose magnetosphere is processing incoming solar wind more efficiently than it does at most other points in the year. The same CME that would produce a KP index of 5, a moderate geomagnetic storm, arriving in mid-July, might produce a KP of 6 or 7 arriving in early April. The same event, amplified by geometry. It is worth being precise about what the Russell-McPherron effect does and does not do, because the distinction matters for how we interpret the convergence. It does not change the probability of a solar event. The Sun does not know what time of year it is. AR4401's magnetic complexity is not influenced by Earth's orbital position. The comet's perihelion distance is not affected by the equinox. The probability that the Sun produces a significant flare or CME in the next 7 days is determined entirely by solar physics, by the state of the active region, the configuration of the coronal field, the dynamics of the plasma at the solar surface. The equinox has no input into any of that. What the equinox effect does is amplify the terrestrial consequences of whatever the Sun produces. It is a multiplier on the output side of the equation, not the input side. And in a scenario where the input side is already elevated, where we are already dealing with a growing beta-gamma active region at disk center, 6 days of persistent electron flux elevation, an inbound high-speed stream, and a large comet approaching perihelion, a multiplier on the output is not a minor detail. It is the variable that determines whether a significant solar event becomes a manageable space weather disturbance or something that stress tests the systems that modern civilization depends on. Consider the cascading logic. The Sun produces a CME from AR4401 at a probability the forecasters already place at 40% for an M-class event, before any comet interaction is factored in. That CME travels along the Sun-Earth line because the region is at disk center. It arrives at Earth carrying a southward BZ component, which CMEs associated with complex active regions frequently do, because the flux rope geometry of the ejected plasma tends to produce sustained southward field in the leading portion of the cloud. It arrives during the equinox enhancement window, meaning the coupling efficiency is near its seasonal peak. It arrives at a magnetosphere that has already been processing elevated particle flux for 6 days and has less buffering capacity than it would after a quiet week. And it arrives, if the timing falls as the orbital mechanics currently suggest, during a window when 4 human beings are beyond the magnetosphere's protection entirely. Each of those steps is individually supported by current data. None of them requires speculative extension beyond what the measurements show. The chain from solar event to terrestrial consequence runs through a series of amplifying factors that are all simultaneously pointed in the same direction. This is the architecture of the convergence, not a single overwhelming force driving toward a single inevitable outcome, but a series of independent variables, each contributing its own modest enhancement to the overall probability and magnitude of a significant response, aligned in a configuration that makes the system as a whole more sensitive than any individual component would suggest. The comet, the active region, the electron flux, the high-speed stream, the equinox window. Remove any one of them and the picture changes significantly. With all of them present simultaneously, the picture is something that the space weather community has not seen assembled around a single perihelion event in the era of modern solar observation. And the timing alignment does not stop at the boundary of Earth's magnetosphere. It extends to 4 specific human beings whose exposure to everything we have just described is not mediated by a magnetosphere at all, because they will have left it behind. The Russell-McFerran effect amplifies what arrives at Earth's magnetic boundary. Beyond that boundary, there is no amplification needed. There is simply direct exposure, with nothing between the astronaut and whatever the Sun decides to do. That is the final human dimension of this convergence, and it is the one that transforms an extraordinary scientific observation event into something with stakes that are not abstract, not statistical, not distributed across a population of satellite assets and power grid components. It is the one with 4 names attached to it, 4 people, 1 launch window, 1 date. Part 10. Leaving the Shield. Artemis. 2 is the first crewed mission to travel beyond low Earth orbit since December of 1972. Let that date land for a moment. 1972, the last time human beings left the protective envelope of Earth's magnetosphere and travelled into the unshielded radiation environment of deep space. Richard Nixon was president. The Vietnam War had not yet ended, and the device you're listening to this on did not exist in any form recognisable to the people alive at the time. 53 years have passed. 2 generations of astronauts have lived entire careers without ever leaving the bubble. And now, in a launch window that opens on April 1st and closes around April 6th, 4 people are preparing to do what no human being has done in more than half a century. Their names are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, representing NASA and the Canadian Space Agency. They will fly a free return trajectory around the Moon, arcing out to a maximum distance of approximately 370,000 kilometers from Earth before the geometry of the orbit curves them back toward home. The total mission duration is approximately 10 days. From a headline perspective, it is a historic milestone. The return of human beings to cislunar space, the first crewed test of the Orion spacecraft in the environment it was designed for, a critical step in the architecture of sustained lunar exploration. From a space radiation physics perspective, it is something more specific and more sobering. It is the first time in 53 years that human beings will be outside the magnetosphere during a period of solar maximum, with an active region at disk center, during an equinox coupling window, in the same week that a large intact comet reaches perihelion on the Sun it is orbiting. But let's build this properly, because the radiation environment beyond the magnetosphere is something that most people have never had a reason to think carefully about, and the gap between intuition and reality here is significant. When astronauts travel to the International Space Station, they are in low Earth orbit, approximately 400 kilometers above the surface, well within the magnetosphere's effective protection zone. The magnetosphere extends roughly 60,000 kilometers toward the Sun, and dramatically further on the night side, forming an elongated teardrop shape carved by the pressure of the solar wind. Inside that boundary, the magnetosphere deflects, captures, and slows the charged particles streaming outward from the Sun. It is not perfect protection. Astronauts on the ISS receive elevated radiation doses compared to Earth's surface, and they are monitored carefully for cumulative exposure. But the magnetosphere is doing enormous protective work on their behalf, intercepting the vast majority of the solar particle flux that would otherwise reach them directly. Beyond the magnetosphere, that protection disappears. Not gradually, not partially. It disappears as a meaningful factor. The magnetopause, the boundary layer where Earth's magnetic field gives way to the interplanetary magnetic field, carried by the solar wind, is a transition zone rather than a hard wall. But once a spacecraft has passed through it and is travelling in interplanetary space, the crew is in direct contact with whatever the Sun is currently producing. Every solar energetic particle event, every high-energy proton stream from a flare, every particle-accelerating shock front driven by a coronal mass ejection, these reach the crew with no magnetic filtering, no deflection, no reduction in flux. The spacecraft structure provides some shielding. The crew can shelter in more heavily shielded sections of the vehicle during an event. But the fundamental physics of the environment has changed entirely from what ISS astronauts experience. The reference case that space radiation physicists return to whenever deep space human missions are being planned is the solar particle event of August 4, 1972. This event occurred in the gap between Apollo 16, which returned in April of that year, and Apollo 17, which launched in December. In that gap, no crew was in deep space. The timing was fortunate in a way that subsequent analysis made viscerally clear. The August 1972 event produced a solar proton flux that, by the dosimetry reconstructed from instrument records, would have delivered a radiation dose to an unshielded astronaut in deep space, sufficient to cause acute radiation syndrome. The clinical condition that results from high-dose, short-duration whole-body radiation exposure, characterized by nausea, vomiting, immune suppression, and in severe cases, outcomes that do not need to be described in detail to be understood. It would have been a life-threatening event for a crew between the Earth and the Moon. The Apollo spacecraft would have provided some shielding. The aluminum hull, the equipment, the mass of the vehicle itself intercepts some of the incoming proton flux. Estimates of the actual dose inside the spacecraft vary depending on the shielding assumptions used, but the range runs from severe to potentially fatal depending on where in the vehicle the crew was located and exactly how the event's energy spectrum is reconstructed. The honest summary is that August 1972 was a near miss for a program that did not know it was being missed. The astronauts who were safe on Earth that August had no particular reason to feel lucky. The risk of that kind of event was known. Its non-occurrence during crewed missions was to some degree probability operating in the program's favour. Artemis II launches into a solar environment that is meaningfully different from the Apollo-era environment in ways that cut in both directions. On one hand, space weather forecasting and monitoring capabilities in 2026 are vastly superior to what existed in 1972. The NOAA Space Weather Prediction Center, the NASA Space Radiation Teams, the network of solar monitoring spacecraft including SDO, SOHO, Stereo, and the DSCO, VR, and ACE instruments at the L1 Lagrange point. This infrastructure provides real-time solar monitoring and advance warning capability that simply did not exist during Apollo. An event of the August 1972 magnitude would not arrive unannounced today. There would be warning, potentially 30 minutes to an hour from the L1 monitors, potentially longer from earlier flare and CME detection. That warning time allows for shelter protocols, for crew positioning in the most shielded parts of the vehicle, for mission control to make rapid decisions about trajectory and timeline. On the other hand, Artemis II is launching during solar maximum, into a week when the solar environment is already running above baseline, across multiple independent parameters, with an Earth-facing active region carrying a 40% M-class flare probability that is growing rather than decaying, during an equinox coupling window in the same period as a large comet's perihelion passage at the Sun. The Apollo missions operated during a different phase of the solar cycle, and the specific convergence of factors currently present was not a feature of any Apollo deep space transit window. The launch window for Artemis II spans April 1st through approximately April 6th. April 4th sits near the center of that window. Depending on the specific launch date selected and the trajectory profile, the crew could be crossing the magnetopause, leaving Earth's magnetic protection behind, on April 3rd or 4th, placing them in the unshielded interplanetary environment precisely as the comet reaches perihelion, and as the CME travel time window from any perihelion-associated solar event begins. If a coronal mass ejection is produced by AR 4401 on April 4th, its travel time to Earth at typical CME velocities is 1 to 3 days. That places the arrival window at April 5th through 7th. A crew that launched on April 4th would be in deep space, beyond the magnetosphere, for that entire window. None of this means the mission should not launch. That point deserves to be stated clearly and without qualification. The people making the launch decision at NASA are not operating without information. They have access to real-time solar monitoring data, to detailed space weather forecasts, to risk modelling that factors in the crew's radiation exposure budget across the full mission duration, and to abort and shelter protocols designed specifically for elevated solar activity scenarios. The flight surgeons and space weather integration teams at Johnson Space Center have spent years preparing for exactly the kind of decisions that a solar maximum deep space mission requires. They are not flying blind. What they are flying into is a week where the baseline of expected solar behavior, the statistical distribution of solar activity against which mission risk is normally assessed, may not fully capture the specific configuration currently present. Mission planning uses historical solar behavior distributions to model radiation risk. Those distributions reflect the full range of solar maximum activity across multiple cycles. What they do not specifically account for is the simultaneous presence of a large intact sungrazer at perihelion, an Earth-facing beta-gamma active region in a growth phase, 6 days of persistent electron flux elevation, an inbound coronal hole stream, and a post-equinox geomagnetic coupling enhancement, all concentrated in the same 7-day window. That specific combination is not well represented in the historical distribution. It may fall within the range the planning accounts for. It may sit at the edge of it. Whether it falls inside or outside the modelled range is a question that the next several days will answer in real time. The comet arrives on April 4th. The astronauts may be leaving on April 4th. The CME window, if any event is produced, opens on April 5th. The crew would be beyond the magnetosphere for the duration of it. If those facts are not yet in the same conversation in the public discourse around this mission, they belong there. Not to generate alarm, not to suggest that the mission planners are unaware of the solar environment, but because the convergence of variables we have been tracking throughout this story does not stop at the magnetopause. It follows the crew past it, and 4 people travelling beyond Earth's magnetic shield for the first time in 53 years deserve to have every relevant variable named clearly, in the open, where it can be examined without distortion in either direction. The comet does not know the astronauts are coming. The Sun does not know the launch window is open. The orbital mechanics that produced the perihelion date and the mission planning that produced the launch window operated entirely independently of each other. And yet here, on April 4th, they arrive at the same moment together. That is not design, that is convergence. And the next thing it asks us to consider is whether there are other signals in the surrounding data, quieter ones, easier to dismiss, but worth placing on the table before we arrive at April 4th without having looked at everything the picture contains. Part 11. The overlap problem. In complex risk analysis, there is a concept called correlated risk. It does not get discussed much outside of actuarial tables, engineering safety reviews, and the kind of quiet, unglamorous meetings where professionals whose job is to think about failure modes sit around and ask uncomfortable questions. But it is one of the most important concepts in understanding why certain events, when they occur, produce consequences that seem disproportionate to any individual contributing factor, and why the standard tools for assessing risk can underestimate danger in specific, predictable circumstances. The basic definition is this. Correlated risk is the condition where multiple independent risk factors, rather than being randomly distributed across time and space, happen to cluster together. And the reason correlated risk is more dangerous than the same total quantity of uncorrelated risk is not complicated once you see it clearly. When risk factors are distributed randomly, when bad things are spread across a timeline rather than concentrated at a point, the natural averaging effect of that distribution acts as a buffer. The probability that all of them peak simultaneously is low. The system gets stressed by one factor at a time, absorbs it, recovers, and faces the next one from a position of relative equilibrium. The total exposure over time may be identical to the correlated case, but the peak stress at any single moment is dramatically lower. When risk factors correlate, when they cluster, that buffer disappears. The system faces multiple stresses simultaneously, each one reducing its capacity to absorb the others, each one arriving before the recovery from the previous one is complete. The mathematics of correlated risk shows that the probability of a severe outcome scales non-linearly with the degree of correlation. 2 independent risks of 10% each, uncorrelated, combine to produce roughly a 19% probability of at least one occurring and a 1% probability of both occurring simultaneously. 2 risks of 10% each that are perfectly correlated, that always occur together or not at all, produce a 10% probability of both occurring simultaneously. The correlation does not change the individual probabilities, it changes what happens when they stack. Now apply that framework to the Artemis II mission and the week of April 4th. Under normal circumstances, by which we mean a solar maximum week with no particular anomalies, no unusually complex active regions at disk center, no large intact sungrazer approaching perihelion, no persistent multi-day electron flux elevation, the Artemis II mission faces a solar radiation risk profile that mission planners have modelled carefully and found acceptable. Solar particle events happen regularly during solar maximum. Some of them are significant. The mission planning accounts for this through a combination of launch window flexibility, real-time solar monitoring integration, shelter protocols that position the crew in the most heavily shielded sections of the Orion vehicle during elevated activity, and abort decision frameworks that define the conditions under which mission controllers would direct an early return. The risk is real, non-zero, and present throughout the mission duration, but distributed across 10 days of solar maximum activity that, while elevated compared to solar minimum, follows a statistical distribution that mission planners have modelled against decades of observational data. The risk is tractable. The peaks are manageable because they are expected to be isolated, to occur against a recovering background, to arrive as individual events rather than as a synchronized cluster. What April 4th introduces is the possibility, not the certainty, not even the probability in the conventional sense, but the meaningful possibility, that the risk profile for the specific window of April 4th through 7th is not drawn from that normal distribution. It is a window where multiple factors that are normally independent have become correlated by timing, producing a concentration of risk that the standard distribution-based modelling may not fully capture. Walk through the correlations explicitly, because this is where the argument lives. The comet's perihelion on April 4th is not an independent random event relative to the current state of solar activity. It is a fixed orbital event arriving at a moment when solar conditions are already measurably elevated. The comet does not make the Sun more active by its mere approach. The Sun's activity level is driven by its own internal dynamics. But the perihelion event, and any plasma injection or trigger effect associated with it, arrives into a system that is already carrying reduced margin. An injection event on a quiet Sun would encounter a system with full buffering capacity. The same injection event on a Sun that has been running elevated for 6 days, with a growing beta-gamma active region at disk center, encounters a system that has already used some of that capacity. The outcomes are not drawn from the same distribution. The AR4401 activity is not independent of the electron flux elevation. Both are expressions of the same underlying solar state, a Sun at solar maximum running hot across multiple simultaneous parameters. The electron flux elevation did not cause the active region's complexity, and the active region's complexity did not cause the electron flux elevation. But they are not statistically independent in the way that two coin flips are independent. They are correlated outputs of the same underlying input, a Sun that is, right now, in an elevated energetic state, across the full range of its observable outputs. When you observe elevated electron flux in a complex active region simultaneously, you're not observing two independent draws from a probability distribution. You're observing two symptoms of the same condition. Treating them as independent in a risk calculation double counts the independence and underestimates the probability that both will contribute to an acute event simultaneously. The equinox effect is not independent of the solar event probability in the way that matters for consequence assessment. The Russell-McFerrin enhancement does not change what the Sun does, but it changes what Earth experiences when the Sun does it. For a crew beyond the magnetosphere, the equinox effect is irrelevant in the direct sense. They are already outside the system the equinox modulates. But the equinox window affects the severity of the geomagnetic environment that any returning crew would re-enter, and it affects the intensity of the space weather response that ground-based infrastructure experiences during the same window. The equinox is a multiplier on consequences, and it is active during the same window as all the other factors. For a crew beyond the magnetosphere during this specific window, the abstract language of risk factors and probability distributions resolves into something concrete and operational. A significant solar particle event, whether produced by AR4401 independently, by a trigger interaction with the comet's plasma injection, by the arrival of the coronal hole high-speed stream, or by some combination, is not, for that crew, a number in a risk model. It is an emergency. The question of when to shelter, where to shelter, how long to remain in the shelter configuration, what the dose rate is in real time, whether the event profile suggests a brief spike or a sustained multi-hour exposure, whether the mission timeline needs to be compressed to return the crew to the magnetosphere's protection more quickly. These are not hypothetical planning scenarios. They are decisions that have to be made in real time, by flight controllers working from incomplete information, under time pressure that does not accommodate extended deliberation. The shelter protocol for Orion in a solar particle event is defined. The crew moves to the most shielded section of the vehicle, which in Orion's case involves positioning near the center of mass, surrounded by the maximum available mass of equipment and structure. This provides meaningful shielding against lower energy protons. It provides less protection against the highest energy component of a major solar particle event, the component that penetrates spacecraft structures more effectively. The degree of protection depends critically on the energy spectrum of the event, on how the particle flux is distributed across energy levels, which cannot be fully characterized until the event is underway and the monitoring instruments are reading it in real time, 15 to 60 minutes. That is the approximate advance warning time available from the L1 monitors, the ACE and Discover spacecraft positioned 1.5 million kilometers sunward of Earth, before a CME's leading edge reaches Earth's orbital distance. For a crew already in deep space, the warning time before the particle flux reaches them may be shorter or longer, depending on their position relative to the field line connecting them to the event source. It is not a comfortable margin for a crew that needs to physically relocate within the vehicle, secure loose equipment, and prepare for an extended shelter period that might last hours. None of this is an argument against the mission. The people making the launch decision have modelled these scenarios at a level of detail that no outside analysis can replicate, using data that is not public, through processes refined by decades of human spaceflight experience. They know what the August 1972 event looked like. They know what solar maximum statistics say about event frequency and magnitude. They know the Orion vehicle's shielding characteristics across the energy spectrum of interest. They are not unaware of the current solar environment. The decision to fly, when it is made, will reflect a judgment by qualified professionals that the risk is acceptable given the full context, including context not available to this analysis. What this analysis can do is name the correlation clearly. The comet is not the story by itself. The active sun is not the story by itself. The astronauts are not the story by themselves. The equinox is not the story by itself. The electron flux elevation is not the story by itself. The story is the correlation, the fact that all of these factors, each one generated by completely independent physical and institutional processes, have assembled around the same 7-day window without design, without coordination, without any causal connection to each other except the shared date they happen to occupy. Nobody scheduled this. No one looked at the comet's orbital mechanics and chose to open the Artemis launch window to coincide with perihelion. No one arranged for AR 4401 to reach beta-gamma complexity in the week before April 4th. The electron flux did not consult the mission manifest before deciding to run elevated for 6 days. The equinox occurs on the same date every year, regardless of what the Sun or any spacecraft is doing. These things assembled themselves into the same window through the operation of entirely separate physical laws acting on entirely separate systems. That is what makes April 4th something other than an ordinary day. Not that disaster is certain, not that the risk is unacceptable, but that the density of simultaneously elevated variables concentrated around a single date, variables that are normally distributed across time in a way that prevents them from stacking, has reached a level that the modern era of solar observation and human spaceflight has not previously seen assembled around a single perihelion event. The convergence did not announce itself, it simply arrived. And now that it is here, there are a few more signals in the surrounding data that belong in the picture. Quieter ones, easier to dismiss, but worth placing on the table before we reach the date itself and lose the chance to have looked at everything the system was showing us. Part 12. Fireballs, Noise, or Signal. In the weeks leading up to April 4th, something else has been unfolding quietly in the background. On its own, it would be easy to dismiss. On its own, it would have a straightforward explanation, but when placed alongside everything else happening in this same window, it becomes harder to ignore. There has been a short series of fireball events, not 1 or 2 isolated sightings, but a cluster compressed into just a few days. On March 17th, a fireball was reported over Ohio. On March 21st, another was observed over Houston. Then on March 23rd, a second event occurred over Ohio again. These events are not speculative. They are documented and verified through observational networks such as the American Meteor Society. They represent real atmospheric entry events, objects entering Earth's atmosphere at high velocity, producing visible streaks of light, fragmentation, and in some cases sonic booms that were heard across wide regions. Under normal circumstances, this would not be unusual. Earth is constantly bombarded by small debris. Every single day, material from space enters the atmosphere. Most of it is tiny, dust grains and small particles that burn up instantly and go completely unnoticed. Occasionally, larger objects enter, producing bright fireballs that can be seen over hundreds of kilometers. These events are part of the natural background activity of our planet moving through a debris-filled solar system. However, Clusters like this tend to attract attention. Human perception is naturally tuned to recognize patterns, and when events that are usually spread out begin to appear close together in time, they feel connected. That perception can be powerful, even when the underlying cause is entirely random. The most straightforward explanation for this cluster is statistical clustering. When random events are distributed over time, they do not appear evenly spaced. Instead, they tend to group together in bursts. There will be periods where several events occur close together, followed by long stretches where very little happens. This is not evidence of a shared cause. It is a natural property of randomness itself. It is the same reason you can flip a coin multiple times and occasionally get a streak of heads or tails. The coin has not changed. The probabilities have not changed, but the outcome appears patterned in the short term. Meteor observation records show this behavior clearly. When viewed over long periods, fireball occurrences average out to a relatively steady rate. But when examined over short windows, the distribution becomes uneven. Some weeks are quiet, others appear unusually active. The current cluster fits comfortably within that statistical framework. There is another factor that reinforces this effect, and that is observation bias. During periods when public awareness of space-related events increases, people pay more attention to the sky. They are more likely to notice unusual phenomena. They are more likely to record and report what they see. As a result, the number of documented events increases, even if the actual number of events has not changed at all. Right now, awareness is elevated. There is an incoming comet drawing attention. There is increased discussion around solar activity and space weather. These factors encourage more people to look up, to record, and to share observations. That creates a feedback loop where the data becomes denser, not because reality has changed, but because perception has. From a scientific standpoint, these two explanations, statistical clustering and observation bias, are sufficient. They account for the observed pattern without requiring any additional mechanism. They are consistent with historical data, and they align with what we understand about meteor activity and human reporting behavior. However, there is another idea that has emerged in some corners of the discussion. It is important to address it, but it must be framed clearly. It is speculative, it is not supported by mainstream planetary science, and it does not have an established physical mechanism. The idea suggests that changes in Earth's magnetic shielding during solar maximum could alter how small incoming objects interact with the planet. The argument is that the magnetosphere, the magnetic field surrounding Earth, is currently under increased stress due to heightened solar activity. At the same time, Earth's magnetic field has been gradually weakening over long timescales, with features like the South Atlantic anomaly expanding and the magnetic poles drifting. According to this hypothesis, the combination of long-term weakening and short-term compression could reduce the magnetosphere's effectiveness, allowing small objects to penetrate deeper into the atmosphere before breaking apart. In theory, this would not increase the number of incoming objects, but it could make them more visible, producing brighter fireballs and more dramatic atmospheric entries. It is an interesting concept, but it has significant problems. The magnetosphere primarily interacts with charged particles, such as solar wind and cosmic radiation. It does not act as a barrier for solid objects like meteoroids. A rock entering the atmosphere is governed by gravity, velocity, and atmospheric density. Its interaction with Earth's magnetic field is negligible in this context. Additionally, there is no well-established mechanism in the scientific literature that links changes in geomagnetic field strength to increased penetration depth of meteoroids. Historical data also does not show a clear relationship between solar maximum periods and increased fireball activity. For these reasons, this hypothesis remains on the fringe. It is not part of accepted scientific understanding, and it should not be treated as a likely explanation. It can be acknowledged as an idea, but it does not carry evidential weight. So, if the fireball cluster is most likely explained by randomness and observation bias, why does it matter at all? On its own, it doesn't. If this were the only thing happening, it would be a minor footnote, a brief spike in reports, nothing more, but it is not happening in isolation. At the same time these fireball events are being recorded, a much larger and more consequential event is unfolding. A large sun-grazing comet, Comet C/2026 A1, MAPS, is entering the final phase of its approach toward the Sun. It has not fragmented. Its light curve remains smooth. Its nucleus appears intact as it moves toward one of the most extreme environments in the solar system. The Sun itself is not quiet. It is near the peak of its activity cycle. Magnetically complex regions are forming and evolving. Radiation levels in near-Earth space have been elevated for several consecutive days, indicating a system that is already under stress. And within this same window, for the first time in over 50 years, humans are preparing to leave Earth's magnetic protection. The crew of Artemis 2 is scheduled to travel beyond the magnetosphere, entering a region where exposure to solar radiation is no longer filtered by Earth's magnetic field. Each of these elements can be understood individually. Each has its own explanation. Each fits within known scientific frameworks. But when they occur at the same time, something changes. Because systems are not just collections of independent events, they are networks of interactions. The behavior of the system as a whole cannot always be predicted by analyzing each part separately. A comet entering the solar corona is one event. An active sun is another. Elevated radiation levels are another. Human spaceflight beyond the magnetosphere is another. A cluster of fireball observations is another. Individually, they are unrelated. But when they overlap in time, they form a configuration, and configurations matter. In complex systems, the most significant outcomes often emerge not from a single variable exceeding its limits, but from the interaction of multiple variables operating within normal ranges. It is the alignment, not the extremes, that creates the potential for unexpected behavior. This is what makes the current moment different. Not because any one factor is extraordinary, but because all of them are active at once. That does not mean something dramatic will happen. In many cases, nothing does. Systems pass through these moments without incident. Everything behaves as expected. The alignment dissolves and the window closes. But occasionally these intersections reveal something new. A system responds in a way that was not obvious when each component was considered in isolation. That is why scientists pay attention to moments like this. Not because they expect a specific outcome, but because the conditions for interaction are present. April 4th is not just a date tied to a comet's closest approach to the Sun. It is a point where multiple independent timelines converge. A moment where the behavior of the system as a whole becomes more important than any individual part. And that is what makes this week different from a routine one. Not the fireballs, not the comet, not the Sun, but the fact that for a brief window all of them are active together. And when that happens, the question is no longer just what each event means on its own. The question becomes what they mean together. Part 13. Systems Thinking. The Sun is at solar maximum. Comet MAPS is intact and approaching perihelion. The radiation environment has been elevated for nearly a week. An Earth-facing active region is growing toward threshold. A coronal hole stream is inbound. The equinox enhancement window is active. 4 astronauts have a launch window that overlaps the perihelion date. A cluster of fireball reports sits in the same time frame. Individually, each of these facts is interesting but not alarming. Scientists monitoring each of these signals on its own, in isolation, would not file emergency reports. They would note it, log it, continue monitoring. But systems do not behave like the sum of their isolated components. Complex systems, and the Sun-Earth system is among the most complex in the observable universe, exhibit emergent behavior at intersections. Where 2 independent processes overlap, the outcome is not simply additive, it is interactive. The behavior of a magnetized plasma carrying wave perturbations from 2 independent sources is not the sum of the 2 individual perturbation patterns. It is an interference pattern with regions of cancellation and, importantly, regions of amplification. Rare events in complex systems do not happen in empty space, they happen at intersections. The Carrington event of 1859 did not occur on a quiet sun during a routine solar cycle. It occurred during a period of elevated activity, with a complex active region, preceded by a series of smaller events that had already stressed the system. The event itself, 2 coronal mass ejections in close succession, with the second travelling through the cleared path left by the first, and arriving at Earth in significantly less time than normal, was the product of multiple factors aligning in an unusual configuration. The alignment was not designed, it was not predicted in advance. It was recognised afterwards as a convergence of factors that individually would not have produced the same outcome. What April 4th represents, in the systems thinking framework, is a convergence. Not a guarantee, not even a high probability, but a moment where the density of simultaneously elevated variables is high enough that the probability of an emergent outcome, something that would not arise from any single factor alone, is meaningfully higher than baseline. That is what we should be watching. Not the comet, not the active region, not the electron flux, not the astronauts. All of it simultaneously, as a system. Because the system is the thing that has the potential to surprise us. And the surprise, if it comes, is not going to announce itself in advance. Part 14. What we're actually watching. Let's take a step back from the details and state clearly what this event actually is and what it is not. This is not a prediction of disaster. This is not a forecast of catastrophe. There is no scientific authority, no credentialed solar physicist, no space weather agency, no NASA spokesperson currently predicting that comet maps will trigger a civilization-threatening solar event. The most likely outcome of April 4th, considered in cold probability terms, is that the comet reaches perihelion, undergoes some combination of fragmentation and vaporization, produces interesting imagery from solar observatories, and the Sun continues on its current trajectory with or without a flare from AR 4401 that would have been within its normal probability range regardless. That is the most likely outcome. It should be stated clearly and repeated as needed. The baseline probability of a routine outcome is higher than the probability of a non-routine one. What this event is, however, is a convergence. That word has a specific meaning. A convergence is not a crisis. It is a moment where multiple independent processes, each evolving according to its own dynamics, arrive at the same location in space or time simultaneously. The significance of a convergence is not that it guarantees a particular outcome. It is that it concentrates variables in a way that elevates the probability of outcomes, including both favourable and unfavourable ones, that would not arise if the variables were distributed across time and space at their normal density. The variables we have been describing over the course of this video are real. Each individual measurement is real, the electron flux data is real, AR 4401's magnetic classification is real, the equinox timing is real, the Artemis II launch window is real, the comet trajectory is real. None of these have been constructed or selected to build a narrative. They are what the data says. And what the data says is that an unusual number of independently significant factors are pointing at the same 7-day window. The scientific meaning of a timing event, as distinct from a size event, is that the outcome is determined more by when something happens than by how large it is. A large comet arriving at a quiet, magnetically relaxed sun in the depth of solar minimum would be scientifically interesting but physically unremarkable. The same comet arriving at a sun near solar maximum, with a complex active Earth-facing region in a growth phase, in a radiation environment that has been running elevated for nearly a week, during an equinox coupling window, while 4 astronauts are crossing the magnetopause boundary, is a different event. Not because the comet is different, because the context is different, because the timing is different. This is what scientists are actually watching when they pay attention to April 4th. Not the comet in isolation. The system, the timing, the intersection, and the intersection is real, whether or not anything remarkable happens when we arrive at it. Part 15. The Aftermath Window. After April 4th, the question does not immediately resolve. A coronal mass ejection produced by an event on April 4th travels at velocities typically between 300 and 2,000 kilometers per second. At average speed, the transit time from Sun to Earth is 2 to 3 days. That places the primary impact window, if any CME is produced, between April 5th and April 7th. That is the period during which Earth's magnetosphere would first encounter any solar ejecta driven by activity around the perihelion event. The observation campaign that begins now and runs through that window is, in the most direct sense, the experiment. SOHO's LASCO coronagraph will have direct imaging of the comet's passage through the solar corona. Stereo provides a second vantage point. SDO's suite of extreme ultraviolet instruments will image any flare activity from AR 4401 in real time. Ground-based magnetometers around the world will record geomagnetic disturbance levels as they develop. The ACE and DSCO VR spacecraft at the L1 Lagrange point, the gravitational balance point between Earth and the Sun, approximately 1.5 million kilometers from Earth, will provide approximately 15 to 60 minutes of advance warning for any incoming CME by detecting the leading edge of the solar wind perturbation before it reaches Earth. The specific signals to watch in the days immediately following April 4th are: first, any sudden brightening or asymmetry in the comet's light curve in the final 24 hours before perihelion, which would indicate late-stage fragmentation. Second, any intensity change in SDO's imagery of AR 4401, concurrent with or immediately following the perihelion moment. Third, any CME detection in LASCO coronagraph imagery in the 6 to 12 hours after perihelion. And fourth, any escalation in the KP index beyond current forecasted levels in the April 5th to 7th window. The absence of any of these signals would itself be scientifically meaningful. A large intact comet passing through a magnetically complex corona without leaving any measurable trace would place constraints on the trigger hypothesis and on models of comet-corona interaction generally. A null result is not a boring result, it is data. The presence of any of these signals in the right sequence and timing would raise a different set of questions. Not proof of causation, correlation and causation remain separate problems even after the event, but evidence for a physical connection that would demand further study. The gap between "we observed a sequence of events" and "we understand why that sequence occurred" is where most of solar physics currently lives. April 4th is not going to close that gap, but it may provide the most directly observable data point this hypothesis has had in the modern observational era. What the solar system is doing right now, assembling these factors around a single date through purely natural dynamics, is something that happens without design, without intention, and without announcement. The convergence does not know it is a convergence. The comet is not aware of the active region. The astronauts are not travelling toward a solar event that they know they are coming. The equinox does not coordinate with the electron flux, and yet here we are, 7 days from a moment where all of these threads arrive at the same point. Science does not traffic in certainty about events before they happen. It traffics in probabilities, in mechanisms, in carefully maintained uncertainty. The honest statement about April 4th is that we do not know what will happen. We know what the inputs are. We know what the physics says about how those inputs can interact. We know what the historical correlations suggest about outcomes when this configuration has appeared before, and we know that the next several days will generate data that will inform how we understand these interactions for years to come. We are watching a system at a moment of maximum interaction, a system that is loaded, coupled, and entering a convergence window that nothing in the modern observational record has assembled in quite this configuration before. After it's over, we will know what it was. We will run the analysis, compare the outcomes to the predictions, update the models, file the papers, and move on to the next question that the universe decides to ask without warning. But right now, we are in the window before the answer exists. The comet is still intact, the sun is still loaded, the clock is still running, and we won't know what this was until after it's over.